Consider a steam power plant operating on an ideal reheat Rankine cycle. The steam enters the high pressure turbine at 30 bar and 350 degrees Celsius. After the expansion to 5 bar, the steam is reheated to 350 degrees Celsius and then expanded in the low pressure turbine to a condenser pressure of 0.075 bar. That is the condenser pressure of 0.075 bar. Determine the thermal efficiency of the cycle and the quality of the steam at the outlet of the low pressure turbine. Okay, we have to find the thermal efficiency and the quality of the steam at the outlet of the low pressure turbine. Given the steam enters the high pressure turbine at 30 bar and 350 degrees Celsius. 1 and 2 is the high pressure turbine and the pressure at point 1 is equal to 30 bar and it is superheated to a temperature of 350 degrees Celsius. This is the superheated line and it is being heated to a 350 degrees Celsius. And after the expansion process, the steam is reheated to 350 degrees Celsius. And this is the expansion process from 1 to 2. The steam gets expanded from 1 to 2 and the pressure at point 2 is given as P2 is equal to 5 bar. And again, after expansion, it is superheated or it is reheated to a temperature of 350 degrees Celsius. It is again reheated to a temperature of 350 degrees Celsius and this is the inlet of the low pressure turbine. And in the low pressure turbine, the steam gets expanded to a condenser pressure of 0.075 bar. That is at P4, the pressure is equal to 0.075 bar. This is the expansion process. 3 to 4 is the expansion which is taking place in the low pressure turbine. Okay. Therefore, this is the work done by the turbine at the low pressure and 1 to 2 is the work done by the turbine at high pressure. That is, this is the high pressure turbine and 3 to 4 is the low pressure turbine. With this data, we have to find the thermal efficiency of the cycle and quality of the steam at the outlet of the low pressure turbine. Quality of the steam is nothing but the dryness fraction at the state point 4. At the state point 4, we have to find x of 4. We have to find this value. Okay. Given from the question, given we have P1 is equal to 30 bar and T1 is equal to 350 degrees Celsius and the value of P2 is equal to 5 bar and we also have the value of P4 is equal to 0.075 bar. The value of P3 is equal to P2 since the heat is being added at constant pressure. Okay. To find we have to find the value of the efficiency of the reheat cycle and the dryness fraction at point 4. That is, at state point 4, we have to find the dryness fraction value, which is nothing but the quality of the steam. Now, moving on to the solution. The efficiency, that is, the efficiency of the reheat is given as the efficiency of the reheat Rankine cycle is given as H1 minus H2 plus H3 minus H4 divided by H1 minus H6 plus H3 minus H2. Okay. In this equation, we have to find all the values of the enthalpy at all the state points. That is, The value of H1, H2, H3, H4 and H6 are all unknown. We have to find all these values in order to calculate the efficiency of the reheat Rankine cycle. Okay. From the superheated steam table, from superheated steam table, superheated steam table, at P1 is equal to 30 bar and 350 degrees Celsius, the value of H1 is equal to 3115.3 kilojoule per kg and S1 is equal to 6.7428 kilojoule per kg. We have find out the value of H1 from the steam table. And from the saturated steam table, that is from saturated steam table at pressure P2 is equal to 5 bar, we can get the value of Sg2, which is equal to 6.821 kilojoule per kg Kelvin, and Sf2 is equal to 1.8607 kilojoule per kg Kelvin. Sfg of 2 is equal to 4.9606 kilojoule per kg Kelvin, and Hf2 is equal to 640.23 kilojoule per kg, and the value of Hfg of 2 is equal to 2108.5 kilojoule per kg. This value is being taken from the saturated steam table. Since the temperature at the state point 2 is a saturated temperature, we are taking the values from a saturated steam table at pressure P2, which is equal to 5 bar. Since the value of Sg2, the value of Sg2 is greater than S1, the steam is in wet condition. That is, the steam is in wet condition since the value of Sg2 is greater than S1. That is, the value of Sg2 is greater than S1. So, the steam is in wet condition. The steam is in wet condition. Wet condition. So, we have to use the equation S1 equal to S2, which is equal to Sf2 plus X2 into Sfg2 in order to find the dryness fraction at the state point 2. Okay, we have to find the dryness fraction at the state point 2 in order to find the enthalpy at the state point 2, since in the enthalpy equation the dryness fraction is unknown. This S1 is equal to S2 is being written as, since the expansion process from the state point 1 to state point 2 is an isentropic expansion process, that is from 1 to 2 the expansion is an isentropic process, S1 is equal to S2. We have the value of S1 is equal to 6.7428, therefore it can be equated to S2 in order to find the dryness fraction X2. Okay. the value of S1 is nothing but 6.7428, which will be equal to SF2 we have calculated from the steam table as 1.8607 plus X2 is unknown into SFG2 value is again 4.9606, and SF2 and SFG2 is taken from the steam table, and from this the value of X2 is being calculated as 0.98. The value of X2 is being calculated as 0.98, and with this value you can find the value of H2. That is, the H2 is given by the equation HF2 plus X2 into HFG2. All the three values are known. That is, HF2 and HFG2 is taken from the steam table, and the value of X2 we have calculated. By applying all this value, you can find the value of H2. That is 640.23 plus 0.98 into 2108.5. By calculation, the value of H2 will be equal to 2706.56 kilojoule per kg. And in the efficiency equation, we have find the value of H1 and H2. Now we have to find the value of H3. That is, we have to find the value of H3. H3 can be founded from superheated steam table. That is, this is the state point 3, and it is being superheated to a temperature of 350 degrees Celsius. So the enthalpy and entropy at the state point 3 can be found from the superheated steam table, and from the superheated steam table at 350 degrees Celsius and 5 bar, that is from superheated steam table at 5 bar and 350 degrees Celsius, the value of H3 is equal to 3167.7 kilojoule per kg, and S3 is equal to 7.6329 kilojoule per kg Kelvin. Now we have the value of H3. Next, we have to find the value of H4. That is, in the numerator, we have H1, H2, and H3. Now we have to find the value of H4, and the state point 4 is in the saturated curve. Okay, saturated vapor curve. So we have to find the value of H4 from the saturated steam table at pressure 0.075 bar. Since the pressure at point 4 is 0.075 bar, we have to calculate the pressure with respect to this pressure from the steam table, saturated steam table. Okay, from saturated steam table at 0.07 bar, the value of HF4 is equal to 168.79 kilojoule per kg. SF4 is equal to 0.5764 kilojoule per kg, and VF4, that is specific volume at the state point 4, is 0.001008 meter cube per kg, and the value of HFG of 4 is equal to 2406 kilojoule per kg, and SFG of 4 is equal to 7.675 kilojoule per kg Kelvin. And all these values are taken from the steam table. Now with these data, we have to find the value of H4. And the value of H4 can be calculated from the equation H4 is equal to HF4 plus X4 into HFG of 4. In this, the value of HF4 and HFG of 4, we have taken it from the steam table, and the value of X4 remains unknown. First, we have to find the value of X4. This value of X4 can be calculated by equating the entropy equation. And again, we know that the value of S3 is equal to S4. Since the expansion process is taking place isentropically, the entropy at the state point 3 will be equal to the entropy at the state point 4, which is equal to SF4 plus X4 into SFG of 4. In this, we have the value of SF4 and SFG of 4. Only X4 remains unknown. So we can calculate the value of X4 by equating this equation, and S3 as calculator is 7.6329, that is 7.6329, which is equal to SF4 is 0.5764, 0.5764 plus the value of X4 is unknown into SFG of 4 is equal to 7.675. From this, the value of X4 is being calculated as 0.919, and this is the dryness fraction value at the state point 4. And we have find out the value of the quality of the steam at the end of low pressure turbine, and this is the dryness fraction of the steam. Dryness fraction of the steam at the end of LP turbine. And we have find out the value of X4 by substituting the value of X4 in this equation. You can find the value of H4. Therefore, H4 is equal to HF4 plus X4 into HFG of 4, and HF4 is equal to 168.79, and we have HFG of 4 is equal to 2406. By substituting this value, you can find the value of H4. It is 168.79 plus X4 is equal to 0.919 into HFG of 4 is 2406. And by equating, you have the value of H4 is equal to 2380.89 kilojoule per kg. Now we have find out the value of H4. The only value which is remaining is the H6 value. That is, we have to find the value of H6. This is the only value which remains unknown, and we have to find the value of H6. We have WP is equal to H6 minus H5. This is the work which is done to the feed pump. The work which is done to the feed pump. This is the work which is done to the feed pump, which is nothing but H6 minus H5, since the work is done to the system. And by equating this, you can get the value as P6 V6 minus P5 V5. Okay, and the volume of V5 will be equal to V6. Okay, the volume of V5 will be equal to V6 since the fluid which we are using is water and the water is incompressible. Therefore, the volume remains more or less constant. Therefore, this value V5 is equal to V6 and the equation is being taken as P6 minus P5 into V5, and this V5 is the specific volume. And to note that this value of V5 is equal to Vf4, which is nothing but the condenser pressure, That is, the volume at the state point 4 will be equal to the volume at the state point 5. Since this is at the saturated vapor state, and state point 5 is at the saturated liquid state, we are equating both this equation, and V5 will be equal to Vf4, and we have P6 is equal to P1 and P5 is equal to P4. That is, this both are heat addition and heat rejection process. That is, for a heat addition process, this is from 6 to 1 is the heat addition process, that is heat supplied, and this heat supplied is at the constant pressure. Therefore, P6 will be equal to P1, and 4 to 5 is the heat rejection process. This is the heat rejection process, and it too occurs in a constant pressure process. Therefore, P4 will be equal to P5. So P6 is equal to P1 and P5 is equal to P4. From this, the value of Wp can be written as P1 minus P4 into Vf4. Okay, we have the value of P1, P4 and Vf4, and Vf4 has been taken from the steam table and it is equal to 0.01008 meter cube per kg, and we have the value of Vf4 from the steam table. By substituting all this value, you can calculate the work which is done to the feed pump, which is nothing but P1 is equal to 30 bar, and I am writing it in Newton per meter square, and 30 into 10 to the power of 5 minus 0.075 bar, that is 0.075 into 10 to the power of 5 Newton per meter square into volume is Vf4 is equal to 0.001008, and on calculation you will be getting 3016.44, and the unit will be Newton per meter square for pressure into meter cube per kg for specific volume, and on cancellation you will be getting Newton meter per kg, and Newton meter is nothing but joule, that is joules per kg. Since all the values are in kilojoules per kg, we will be dividing this value by 1000, and you can get the value as Wp is equal to 3.016 kilojoule per kg. Okay, 3.016 kilojoule per kg. And by substituting this value, you can find the value of H6. That is, we have H5 is equal to HF4, which is equal to 168.79 kilojoule per kg. That is, the pressure at the state point 4 and state point 5 are equal, but at the state point 4, the steam is in a dry saturated state, that is, it is in the curve of saturated vapor curve, and the state point 5 is in the saturated liquid curve. Okay, therefore we can equate this both this equation, and H5 is equal to HF4. That is, HF4 is the fluid enthalpy of the fluid. Okay, by substituting the value of H5 and WP in this equation, you can find the value of H6. That is, H6 will be equal to, H of 6 will be equal to WP plus H5, which is nothing but 3.016 plus 168.79, and H6 is equal to 171.806 kilojoule per kg. And now we have all the values for calculating the efficiency of the reheat. So by substituting these values, you can find the efficiency of the reheat Rankine cycle. That is, the efficiency of the reheat Rankine cycle is equal to H1 minus H2 plus H3 minus H4 divided by H1 minus H6 plus H3 minus H2. We have all the values, and substituting these values in this equation, you can find the efficiency of the reheat Rankine cycle. And the value of H1 is 311.5.3 minus H2 is equal to 2706.56 plus the value of H3 is given as 3167.7 minus H4 is 2380.89 upon H1 is again 3115.3 minus the value of H6 is 171.806 plus H3 is equal to 3167.7 minus the value of H2 is 2706.56. By equating, you can get the efficiency of the reheat Rankine cycle as 0.35 or 35%.